Good day, everyone. In today's lesson, we'll be looking at simple harmonic motion, simply called SHM. At the end of the lesson, we will be able to define what simple harmonic motion is, the examples that are involved, and the lead to calculations as well. So let's dive into this. So, what is simple harmonic motion? Now, simple harmonic motion is a type of periodic motion in which an object oscillates back and front around an equilibrium position, with its acceleration directly proportional to its displacement and always direct towards equilibrium. All right, it's called simple because it follows a linear pattern and can be described by a sinusoidal function. So simply put, you can just say that it's a type of motion, it's a type of oscillatory motion that moves to and fro, to and fro, to and fro periodically. When you say periodically, it means that it constantly maintains the time at which it is moving. All right, and this motion is dependent on two major terms, and that is displacement and acceleration. In fact, it has been confirmed that the more the displacement, the more the acceleration. Let us pick an example for instance. Okay, let's say that you pick a pendulum bulb, you suspend it on the ceiling, and you displace it. Imagine a pendulum bulb. Okay, this is the bulb, and this is the string on the pendulum bulb, and then it is being suspended like this on the ceiling. Now, if you displace this pendulum bulb, maybe you take it to this point push it to this point with your hand, and you release it. Let's make it a broken line so that it is just a temporal displacement. Now, if you take it to this point and you release it, it will go bypass the position that it was before, and it will come to this extreme, and then it goes back again like that, back and forth like that. That is what we call simple harmonic motion. So now this displacement here, if it is a very short displacement, okay, the acceleration too will be a small acceleration. But if displacement is high, maybe instead of taking to this length, you are bringing the ball to this point, then the acceleration at which it will move will also be high. That's why we say that the acceleration is directly proportional to the displacement. So the more the displacement, the more the acceleration. And lastly, this motion always moves towards the equilibrium. The equilibrium position is the rest position, the point where it's not moving. So whenever you displace it, it keeps moving to and fro until it returns back to its equilibrium position. And this acceleration is what is directing it toward that equilibrium position. All right. And the acceleration also is dependent on a force called the restoring force. The restoring force is proportional to the displacement, just like the acceleration is proportional to the displacement, because force and acceleration are also proportional, F equal to ma, right? So what means here is that the more the force, the more acceleration. The lesser the force, the lesser acceleration. But in simple harmonic motion, we say that the displacement is proportional to the acceleration. Okay, so if you have more displacement, then you have more acceleration, which means that you have more force, more restoring force. Back to what we drew earlier, if the displacement is much more than before, the restoring force that we want you to come back to this position here will also be more. So the three of them are directly proportional to one another. Okay, displacement is proportional to acceleration, and acceleration is proportional to the restoring force. All right, that bring back that object back to its equilibrium position. Okay, so let's see some of the examples that we have in this simple harmonic motion. One of them is called the loaded test tube. Now this is a test tube here, loaded test tube in a liquid. When you load substance inside this test tube, when we say loaded test tube, that means you have substance in the test tube. The test tube is just a very small tube that is be used in the lab. Now you load it with maybe some object or content. After loading it, you now take the loaded test tube and put it in a liquid. If you put it in a liquid and you press it inside that liquid, it will be moving up and down in that liquid. That up and down movement is also an example of simple harmonic motion. Okay, and it will not continue to move up and down because there is a force called restoring force that will want it to come back to its equilibrium position whereby it will not move again. Okay, so aside from loaded test tube as an example of simple harmonic motion, we also have simple pendulum, which I have explained in the first scenario, that the ball will continue to move up to and fro like that, to and fro like that. Let me quickly take us back there again. To move to and fro like that until you see it here, until it come back to its equilibrium position. So that's another example of simple harmonic motion. We have looked at simple pendulum, and we have also looked at loaded test tube. So aside from simple pendulum and loaded test tube, another one is spiral spring. A spiral spring is another example of simple harmonic motion. It's not just spiral spring, a loaded spiral spring. Okay, on my right hand side, you can see a spiral spring here. This spiral spring now, if you apply a load on it and you displace that load, it will see that the spiral spring will be what? Vibrating up, down, up, down. That up and down movement of the spiral spring is called simple harmonic motion because it is going back and forth, back and forth. Simple harmonic motion, in fact, is a typical example of vibratory motion or oscillatory motion. So going back and forth, but it will not continue that way because a restoring force will make sure that that motion stop after some time. Okay, that restoring force is the causative agent of the stopping of the motion. So it will now bring that object to its equilibrium position. So lastly, we also have the bifilar suspension. The bifilar suspension also behave like the simple pendulum too. When you load it and you displace it, it moves to and fro like simple pendulum, and the restoring force will eventually set in that will bring it to its equilibrium position. All right. So there is a mathematical representation of simple harmonic motion, and here it is here, where you have x equal to capital A sine Wt plus theta. The x there represents the displacement. The A is the amplitude. Amplitude is maximum displacement, okay? Where the W, we've come across W today before in our previous class, that is called angular frequency, angular velocity or angular speed. Sometimes you can also call it angular frequency. The T there, the time it takes that object to move to and fro, and this symbol here, which is phi, is called the phase angle, okay? As the object is moving from one position to the other. The difference between the two positions is called the phase angle. So these together form this mathematical representation of simple harmonic motion. Okay, so this is the omega here. So we call it angular frequency, or we call it angular speed, or angular velocity. In this topic, they are used interchangeably, so don't get it confused. Angular frequency is the same thing as angular speed, the same thing as angular velocity, and the symbol is this W or omega. So W, we said that W has about 8 formulas. In our previous lesson, we've been able to talk about few of the formulas. Aside from the one you have here, we know that we have also said that it is expressed as uh, angular frequency can also be V over R. Angular frequency can also be 2 pi f. Okay, so then of course angular frequency can also be 2 pi n over t. Angular frequency can also be change in angle over time. We have other ones, but for the purpose of this topic, it is very important that you know that these are different formulas for angular frequency. The change in angle over time, 2 pi n over time, where the n is the number of oscillation, then V over R, where the V is linear velocity and R is the radius, then 2 pi f, where f is the linear frequency. Linear frequency is not the same as angular frequency, of course, you could see, but they are related with this formula. All right. So having said that, let us see real world application of simple harmonic motion. Of course, we have listed examples of where it has been applicable. Let us still see the real world application. Now we can find simple harmonic motion playing out in mass spring system. So in mass spring system, when you place mass on it, you see that spring vibrating up, down, up, down. That movement is simple harmonic motion movement. And grandfather clock, in the past there is a clock that has this simple pendulum in it. Okay, when you set alarm, you begin to move to and fro and be making sound, showing that it is already alarm time. So that movement that we observe is simple harmonic. Then tuning fork. Tuning fork is one of the apparatus we use in the physics laboratory to test for sound. Okay, when you strike tuning fork on a table, it begin to vibrate. And that vibration is to and fro as well. That vibration is simple harmonic motion. Then lastly, a child, on a swing. That child, as it go forward and backward, is exhibiting simple harmonic motion as well. Okay, so these are the major four examples that are applicable in our real world. Now let us see one or two questions on this topic. Yeah, I said, what is the frequency of vibration if the balance wheel of a wristwatch makes 90 revolution in 25 seconds? So what is the frequency of vibration if the balance wheel makes? Now, this this is 90 revolution. That means the number of revolution is 90. Let's really solve this question together. But we have to find the frequency. What is the frequency of vibration? We have to find F. So F is unknown. If the balance wheel of a wristwatch makes 90 revolution, so number of revolution, that is our N. Our N is equal to 90. Then in 25 seconds, our T is 25 seconds. Okay. Now by formula, frequency has its own formula to be N over T. Please take note of that. But in terms of relationship with angular frequency, we know that frequency is omega. Frequency is 2 omega over 2 pi. That's the formula for frequency when you want to relate it with omega. But a general formula for it is N over T, where the N is the number of revolution. Sometimes we call it number of circles. Sometimes we call it number of oscillation. So in this case, it is called revolution. That means F is equal to N over T, and that is equal to our N is 90 over T. Our T is 25. Okay. So if you check this on our calculator, 90 divided by 25, so we have it to be 3.6. So 3.6. So the correct option is option D, 3.6 hours. It's not 2.27. It's not 0.04 hours. It's not 0.01 hours. From our calculation here, we have it to be 3.6. So 3.6 is our answer. So you can express as 3.6 hours. Okay, it has 2 units. It can be 3.6 hours, or you can say 3.6 cycle per second. Okay, so either you say hours or cycle per second, it's still the same unit. Okay, now look at this question here. It said the motion of the tire of a moving car, that's I is the motion of the tire of a moving car. Then the motion of a loaded test tube oscillating vertically. Option I, the beating of the heart. IV, a stone tied to a string and wheeled round. V, the motion of the piston in a gasoline engine. Which of the motion above is simple harmonic? So it's very important that you pay attention to the motion of each of these examples. So let's see the first one. The first one we are told the first one is the motion of the tire of a moving car. The motion of the tire of a moving car. Of course, the motion of the tire of a moving car is a linear motion. So I is out of it. We have the motion of a loaded test tube oscillating vertically. So we mentioned this one as an example. So I is correct. Then we also have I, the beating of the heart. The beating of the heart is another example that we didn't mention. It's an example of a simple harmonic motion because the heart also go back and forth. Okay. Then a stone tied to a string and wheel round. This is not simple harmonic motion. This is circular motion. So we've seen I to be correct. We've seen I to be correct. So 2 and 3 are correct. Then number 5, the motion of the piston in a gasoline engine. So the motion of the piston in a gasoline engine also go to and fro. Okay, that's V. So which of the following? So we have A, I, and IV. That's not IV is not correct. So A is wrong. Okay, we have option A to be IV. For the fact that IV is not part of it is wrong. Then B, we have I, I, and V. So for the fact that, okay, let's check. The motion of related with I is correct. Then that is the beating of that is correct. Then V, the motion, okay, B is correct now. Then C, let's check C. We have to go for the most correct one. So we have I is part of it. I is part of it. Then IV is not part of it. So C is wrong. Then D, I is not part of it at all. So the correct option is B. I, and V. All right. So we are going to be doing the cutting here today. I hope you have been able to learn something today from the introduction to a simple harmonic motion. Thank you for listening and have a wonderful day. Bye for now.